folks. Hope you're doing well today. What we want to talk about in this section are exponential functions, and then we'll also define logarithmic functions with bases other than e. So notice the only exponential function we've talked about in calculus is e to the x. So what if we need to talk about, for example, y is equal to 2 to the x power, or y is equal to 1/3 to the x power. Those are also exponential functions, but the base, which is 2 in the first case and 1/3 in the second case, is of course not e. And this definition is a strange definition. Let's go through it. It says if a is a positive real number and a cannot be 1, okay, and x is any real number, then the exponential function to the base a is denoted by, now watch this definition, it says a to the x, just like over here, 2 to the x, your base is 2, your exponent is your variable x, is defined as e, and then raised to the natural log of a times x. Now that seems like an unlikely definition, but since we have defined an exponential function in terms of base e in our calculus class, then to move on to a base other than e, we still need that base e definition in our problem. It says, note if a is equal to 1, then you would have 1 to the x, right? And 1 to the x is actually not an exponential function at all, because it's 1 times 1 times 1 times 1, which is just 1. So that would be called a constant function instead. So that's why we just assume a is not equal to 1, because that's not an exponential function. Okay? Now, we've got some properties here. These are properties that you already know. I know in a pre-calculus algebra class you learned about exponential functions with bases other than e. It wasn't defined this way, but really it is the same old exponential function you know. So if you have like a to the 0, that answer is 1. And again, an example of that is 2 to the 0. We know any value to the 0 power, as long as that base is not 0, okay, is equal to 1. All right? Now, a to the x times a to the I. Remember what you do when you have a common base. You add the exponents. Just like x squared times x to the 3rd is x to the 5th. Well, on the other hand, if you have 2 to the 4th times 2 to the 6th, that's 2 to the 10th. So that's the second property. The third property, a to the x divided by a to the y, is a to the x minus y. So again, an example here. Let's do this in blue. If you have 2 to the 5th divided by 2 to the 3rd, that would be 2 squared, right? And if you had to think about it the hard way, 2 to the 5th is 2 times 2 times 2 times 2 times 2. 2 to the 3rd is 2 times 2 times 2, and you cancel those 3 with those 3, and there's your 2 squared. See what I mean? So that's where that rule comes from, and you know that. And then finally, if you have a power to a power, then you multiply those together. For example, 2 to the 4th raised to the 10th power is just 2 to the 40th. Okay? So properties you already know. And by the way, before I switch pages, those properties can all be proven from this definition right here. I'm going to spare you the gory details because I think you're already comfortable with those properties. But the true way to prove those 4 properties is use the definition that I gave you, which can be done, but we're going to spare us all some time and go ahead and just assume those properties true without proof. Now, while I'm in the middle of defining, let's go ahead and give the definition for a logarithmic function to a base a. Now, in calculus so far, we have only defined a logarithmic function as a natural logarithm, right? So a natural log of x, and you remember how that was defined? That was defined as the integral from 1 to x of 1 over x dx, which had to do with the area under the curve. So everything is based on that definition that we have done in this chapter. So we haven't defined like a log base 2 of x, but notice it's defined in terms of a natural log. So if a is a positive real number, notice a has to be positive, and once again, a cannot be 1, and x is any positive real number, then the logarithmic function to the base a is denoted by log base a of x. That's how you say that, log base a of x, and is defined as log base a of x is 1 over the natural log of a. Remember, that's just a constant, times the natural log of x. Again, that seems to be a strange definition when all I'm really talking about is something like log base 2 of x or log base 5 of x. Those are the functions that we're talking about. And we could, so for example, log base 2 of x would be defined by 1 over the natural log of 2 times the natural log of x. Now, if you'll remember back in your pre-calculus class, you probably talked about a change of base formula. Notice I'm rewriting this as natural log of x divided by the natural log of 2. Remember, we jump straight from there to there. That's called the change of base formula. But we presented it kind of in a backwards way. This is using that as a definition because, again, so far all we have in our toolbox is the natural log of x. Now, there's some properties there as well. These are properties you've seen before. And so the first one is log base a of 1 is equal to 0. Okay, so any logarithm of 1 is 0. Now, what we've had in this class already is the natural log of 1 is equal to 0. Remember, that was based on area from 1 to 1, which was no area at all. But that's true for any log. So log, base 2 of 1 is also equal to 0. We have another property, and we tend to use this as expand or condense. Remember, when you multiply inside a logarithm, you can expand it by saying log base a of x plus log base a of y. So multiplication turns into addition of separate logarithms. Log base a of x to the n, we can move that n in front and multiply. And finally, log base a of a quotient is subtraction of two separate logarithms. Now, what I like to tell students, and I know you remember this, a logarithm is an exponent. Okay, so by definition, a logarithm is an exponent. Actually, not this definition above, but it is true that a logarithm is always an exponent. And that's really where these properties come from if you think about a logarithm in terms of an exponent. Now, once again, I'm going to spare you the proof of these four properties, but the proof would come from using this as the definition. And we have already talked about the properties for natural log, and so that really just extends to these four properties because 1 over natural log of a is just a constant. Okay? Now, before we can finally do some examples, I have 3 more properties for you. These are called properties of inverse functions. Remember, we did an entire section discussing inverse functions. And exponential functions, say 2 to the x, is the inverse of the logarithmic function, which would be log base 2 of x. So these are inverses of each other, and keep that in mind. But first property here, if y equals a to the x, that's called exponential form. You can rewrite that in logarithmic form. X is equal to log base a of y. Now, that's not what I have written here. These are both functions of x, and they are inverses of each other, just like the square root of x is the inverse of x squared. That's what I mean by inverses of each other, okay? But what that above line is saying, for example, if I gave you the equation y is equal to 2 to the x, that's called exponential form. All right, I could write that in logarithmic form. In other words, y is equal to, not y, I'm sorry. Remember, a logarithm is an exponent. It would be x is equal to log base 2 of y. Now, these are saying exactly the same thing. So this is what they call logarithmic form. So those aren't inverses of each other because I switched the x's and y's. Those are identical to each other. All right, property number 2. If you have a to the log base a of x, remember how I just pointed out that log base a and a to the x are inverses of each other? Well, those guys cancel each other out and give you x. Again, it compares to taking the square root of x squared. That answer is x as long as x is greater than 0. Notice this is required here too. You have to say x is greater than 0 because you can't take the logarithm of a negative number. Okay, and then the third property, log base a of a to the x, is also equal to x. It's like that. They cancel each other out to give you x. Again, it's no different than if I switch this around and say the square root of x squared is equal to x. And again, in this case, x has to be greater than 0. Notice here it says this is true for all x. You know why? Because you're not taking the logarithm of a negative number here. A is always a positive value, so those can cancel and give you all x values. Now let's do some examples here. I would like to address this first problem two different ways. Of course, there's one option is you could type that directly in your calculator if your calculator will evaluate log of any base, where you would type the 27 down here and do the 9. My calculator won't do that. Plus, I prefer you be able to do it without a calculator. So then what do? Again, two ways you can do it. You could rewrite this in exponential form. Okay, so what I mean by that, well, the base is 27, so I could say 27. How about let's write it properly, 27. Okay, the answer to a logarithm is an exponent. I don't know what the answer is. So to the x is equal to 9. And then you could rewrite these with a common base. For example, 27 is 3 to the third. That is still raised to the x power. 9 is 3 squared. Then right here, I multiply those together. 3 to the 3x is equal to 3 to the second. And then I solve the equation that I have up here. Since the bases match, I can just say 3x equals 2, or x is equal to 2/3. So the answer to this problem is 2/3. Now, let's just handle it that way. There are other ways you could handle it where you rewrite your 9 with a base 27. But that's not so easy to do for this particular problem, so I think let's just stick with this particular method, besides I'm out of space. And so we have another problem. Let's reinforce it by just doing another one. Okay, so you start with the base. This is a base 4. Okay, to what power? Well, a logarithm is always equal to an exponent. There we go. Is equal to 1 over 64. Now, just like in the red here, I'm trying to write 4 and 1 over 64 with a common base. Now, I know you recognize 64 is 4 to some power, right? Or is it? It is, right? 64 is 4 to the third. So I can say 4 to the x equals 1 over 4 to the third. Now, y'all, that doesn't mean x equals 3 because we're in the denominator. What could we do? Well, we could take that to the numerator. 4 to the x is equal 4 to the negative 3. That's still times 1 up there. This 1's still there, but 1 times 4 to the negative 3 is just 4 to the negative 3. And then from there, I figure out x is equal to negative 3. Okay, you just set exponent equal to exponent, just like we did over here, exponent equal to exponent, and then solve. Okay, so I know my answer is negative 3. Now notice this one just says, problem D just says rewrite. It doesn't say find the answer or anything like that. I'm just simply trying to rewrite this problem. So let's focus on the logarithm. So I could say log, what's the base? Base 27. What's the argument? Now remember, a logarithm is always equal to an exponent. My exponent, it's hard to see it, is 2/3. So log base 27 of 9 is equal to the exponent, which is 2/3. Now notice that's really the same as the first problem. We just rewrote that in logarithmic form. So no solving, just rewriting here. Now to continue really our review, because you should have learned about logarithms with all sorts of bases and exponential functions with all sorts of bases in a pre-calculus algebra class. What's different in calculus is how it's defined, but we didn't do any proof to get the properties, and the properties are exactly the same. And so hopefully you remember a little bit about graphing logarithms. Okay, it's a couple of ways we can handle this. The logarithm is the inverse of an exponential function. Or what we really could do, and this would, I think, make this the easiest. Let's just do a t-table and plug in values. And this log base 3 graph is going to look very similar to a log base 2 graph and to a natural logarithm graph. And you've already graphed a natural logarithm graph in this chapter. So log base 3, what can we plug in? Well, remember, you can't plug in any negatives, so negatives are out because you can't take the logarithm of a negative number. Zero's out because you can't take the logarithm of 0. So where do you start? Now please don't start at 1 because that will not give you what you need. Let's start at 1 but leave some space. Okay, let's plug in 1 and 2 and 3, and if we need to plug in more we will. Okay, so if I plug in 1, what are we saying here? So that would be log base 3 of 1. Now we already have a property that says log, no matter what the base is, of 1 is equal to 0. Okay, then we can evaluate log base 3 of 2. Now, if you have a calculator that will do this for you, then you're good to go. If you have a calculator like my calculator, then you would really need to use the definition of logarithms to do this problem. Or you can think about this as the change of base formula, but here we go. You remember it's natural log of the argument, which is 2, divided by natural log of the base. And then I can just plug that directly into my calculator. Let me tell you what I get. 0.63 is what I got. And then if we plug in 3, I got log base 3 of 3. Okay. Now you know that log base 3 of 3 is 1. If you rewrite that in exponential form, right, it'd be 3 to what power equals 3, right? So 1 would have to be it. But I noticed none of the properties address that. But anytime your base and your argument match right here, the answer is 1. Okay. Now remember I said you have to plug in some numbers between 0 and 1 as well. A good choice would be 1/3. I know you don't see that right now, why that would be a good choice, or you might, so let's check it out. So you'd have log base 3 of 1/3. Okay, now I could rewrite 3, or 1/3, I'm sorry, is 3 to the negative 1. So log base 3 of 3 to the negative 1. Remember, the inverse properties, those cancel each other out to give you negative 1. Hey, it did address that. You could think about that as the inverse property. Those cancel each other out because that exponent is 1 and get 1. So when I plot these, 1/3, let's plot in some cool color, like purple. Okay, so I plug in 1/3 is my x value. So remember that's 5. So 1/3 is way over here and I get negative 1 as an answer. I plug in 1, I get 0. I plug in 2, I get 0.63. I plug in 3, and I get 1. Now I can tell you if you plug in larger numbers, it gradually increases like that, almost like a square root. And then if I plug in numbers here closer and closer to 0, it goes down to negative infinity. Like if I plugged in 1/9, you could rewrite that. You would see you would get negative 2. If I plug in 1/27, you'd get negative 3. So basically this is what a logarithm graph looks like. Log base 3 has the same general shape as log base 4 or 5 or 6. What happens is it doesn't increase nearly as quickly and it doesn't go down to negative infinity, maybe faster or slower, but that's the general shape, very much like a natural log of x. And so I wanted you to see the general shape of these. We will be spending most of our time just taking the derivative of an expression like this and integrating an expression like this, but I just wanted you to be aware of what the graphs look like in case you run into that. All right, folks, so let's talk about the new stuff. We want to talk about the derivatives for bases other than e. So it says let a be a positive real number. So remember the base a has to be positive, and it can't be equal to 1 because if it were 1, it would be a constant function, right? So let a be positive and not equal to 1, and u is going to be a differentiable function of x. Now our first property is just the regular old derivative. Okay, so for example, if I have y is equal to 2 to the x power. Notice the formula says that the derivative of 2 to the x or a to the x is the natural log of a times a to the x. So notation, I can write y primed is the natural log of 2 times 2 to the x. Okay? Not the natural log of x, right? The natural log of 2. So this is just a constant. Remember the derivative of e to the x is just e to the x? So if the base is not e, then you have this extra natural log of the base times your exponential function, okay? So that's the first property, or the first derivative. The next derivative, number 2, is what if you needed to use the chain rule. So this is the same rule as above, so don't think about this as a different rule. What this is saying is if you had something like y equals 2 to the 3x instead, then the derivative, y primed, is going to be, once again, natural log of the base times 2 to the 3x. But don't forget, you have to put times the derivative of your exponent, so times 3, because the derivative of 3x is 3. Now, how would you clean that up? Put the 3 in front. So 3 times natural log of 2 times 2 to the 3x power. And there I go again, doing a printed natural log and a curvy natural log. Let me be consistent. There we go. So all I did was move the 3 right in front. So this is just the chain rule. So whenever you see u's, it means for integrals you need to do a u substitution. For derivatives, it's the chain rule. Okay? Now, I got 2 more of these. Number 3. Now, the derivative of a logarithm. Now, remember, the derivative of y is equal to natural log of x. Remember that? That's just, I almost put equals. That's not right. Y primed is equal to 1 over x. Now, for a different base, like y is equal to log base 2 of x, it's the same thing. It's still 1 over x, but it's times this extra natural log of a in the denominator. So we would have an extra natural log of 2. So think when you have exponential, you multiply by natural log of the base. When you have logarithmic, you divide by the natural log of the base. Okay, so it's not a big stretch, these properties, not a big stretch. And then the fourth and final derivative rule I want to give you is what if you needed the chain rule? So what if I gave you y is equal to log base 3 of, let's say, 6x, right? Then your derivative, y primed, is going to be 1 over 6x. But because it's not a natural log, I have to multiply the denominator by an extra natural log of 3. And I also have to use the chain rule by taking the derivative of the inside, which is times 6. So to simplify that, I'd put y primed is equal to 6 over, and then this is going to be natural log of 3 times 6x. But guess what? That 6 and that 6 cancel, which will give you 1 over natural log of 3 times x. Good with that? All right, so let's do some problems. All right, so for some official problems, here's D. Find the derivative. So proper notation, right, we would write g primed of x is equal to. Now here's what I notice when I look at this. I've got an exponential function. How do I know that? Because I have a variable as an exponent. It's not an e to the x. Remember, the derivative of e to the x is just e to the x. So I need an extra natural log of 2. Because we're taking the derivative of an exponential that's not a base e, you're going to have this extra natural log of 2 that you multiply by. Then times, now how would you take the derivative if that were e to the x? Well, you would say e to the x, so I'm going to say 2 to the negative x. But you know what? I have to use the chain rule. I have to take the derivative of my exponent, which is going to be negative 1. Okay, so when I simplify that, let's put the negative 1 in front. In other words, negative natural log of 2 times 2 to the negative x. And that is completely simplified. Now, I like to put a dot in between there so I can really distinguish the difference between this constant natural log of 2 and this exponential function 2 to the x. See, this is just a decimal. You know, that's not a variable right there. That's just the natural log of 2. You could type that in your calculator, but it's more accurate if you leave it as an exact. So there is the derivative. That's it. That's as good looking as that thing gets. All right, let's try the next one. Now the next one, here's what I want you to notice. This requires the quotient rule. Why? Because there is a function with t in the top. That's your exponential function. But you also have a t in the denominator. So we're going to have to do low d high minus high d low over low squared. You ready for that? So f primed of t. T is not my favorite. Probably not yours either. So I do low, which is t, times the derivative of the numerator. Now again, this is an exponential function with base 3. So I'm going to have this times natural log of 3 business times 3 to the 2t, but I also have to multiply times the derivative of the exponent, so times 2. So again, this is first, and all of this is the derivative of, oh, I didn't say that right. I'm trying to do a product rule. I'm sorry. This is low, and this is the derivative of high. And then minus high, which is 3 to the 2t, times the derivative of low, which is just 1, right? all over rho squared, so t squared. Now it's just about simplifying the expression. Sometimes it's just about writing it in a better order. So notice right here, I have a 2t, okay, and then I have times natural log of 3 times 3 to the 2t minus 3 to the 2t over t squared. My advice is to factor out this common 3 to the 2t out of those two terms, and then I think it'll be about as simplified as we should be. So 3 to the 2t times, so again, I'm factoring out what's highlighted there, that common, and then that's going to be 2. Now, y'all, I'm going to write this as natural log of 3. That t is still there, minus 1 over t squared. And that is the final simplified version of that derivative. So I've got 2 more derivative problems for you. We could probably do them all day long, but it's something you're going to have to practice, right? So first of all, remember, when you have a logarithm, you can expand. If you've got multiplication, division, or exponents inside your argument, that can be simplified before you take the derivative, and I really advise that. So I'm going to say h of x. Notice not h prime of x yet. We're going to simplify this first. So because I'm multiplying right here, I'm going to split that up as addition. And because I'm dividing right here, that's going to be subtraction. So I'm going to have log base 3 of x plus log base 3 of x minus 1 to the 1/2. Right, because it's under a square root, plus log base 3 of 2. And I put plus, and it didn't need to be plus. I just said it needed to be minus, right, because you're dividing. One more thing, this 1/2 can be moved in front of that logarithm. So no derivative yet. H of x is log base 3 of x, parentheses not required there. 1/2, I just said I'm going to move the 1/2 in front and didn't. 1/2 log base 3 of x minus 1 minus log base 3 of 2. Now let's take the derivative. So h prime of x is equal to, now remember, when you take the derivative of a logarithm, you divide by the natural log of the base. So I have 1 over x, because the derivative of natural log is just 1 over x. But since this isn't natural log, I have this extra natural log of 3 that goes in the denominator. You with me? Plus 1/2 is a constant. Okay, so now I got another fraction I'm dealing with. There's my 1/2, right? And then I'm doing 1 over x minus 1. But since this is a log base 3, I have to squeeze in here a natural log of 3. Okay? And then minus, okay, that's multiplication. Minus, this is a constant. Log base 3 of 2 is just a number. There's no variable there at all. The derivative of a number or a constant is just 0, right? So let's make this look a little more attractive. I got h prime of x is equal to 1 over natural log of 3 times x. And again, that 3 could or could not be in parentheses. Plus 1 over 2 times natural log of 3 times x minus 1. Do you know what I forgot? I forgot to take the derivative of the inside right here. Maybe I did. Maybe that's what that 1 was, but the derivative of x minus 1 is 1. Now, it didn't change my answer, but listen, if that was a 2x minus 1, then the derivative of the inside will be 2. Remember, chain rule there. So make sure you follow that. Maybe stop the video and go back and make sure you're comfortable with all of those steps. Okay, and then the last problem, I decided I needed more room on this problem. So notice the directions here say use logarithmic differentiation, and I want to explain to you why. Notice that this is the first problem that we've ever seen in class where we have the base is a variable and the exponent is a variable. So if you have a variable raised to a variable exponent, you're going to have to use logarithmic differentiation. There is no other choice to get the job done. You can't use the power rule because you have a variable as an exponent. Okay? All right, so what do I mean by logarithmic differentiation? Remember, you did this a couple of sections ago where you took the natural log of both sides of your equation before you even took the derivative. So here we go. I'm going to say the natural log of y is equal to the natural log of x to the x minus 1 power. Now, how did that help? Because I can move this x minus 1 exponent in front of my logarithm. Remember, we have one of those 3 rules when you expand or condense that says if you have an exponent, it can be moved in front of the logarithm. And the only time you can do that is when you have a logarithm. So, no derivative yet. Natural log of y is equal to parentheses x minus 1 times the natural log of x. Okay? So, we have simplified the logarithm of both sides. Now it's time to evaluate the derivative. So I'm going to change colors just because this is like another step. Now, when you use logarithmic differentiation, and when you take the derivative of y, remember you have to put times dy over dx. So the derivative of natural log of y is 1 over y, but I have to put times dy over dx because I took the derivative of y with respect to x. This side, I'm going to use the product rule, okay? So this guy right here is the first, this guy right here is the second, right? So I say the first times the derivative of the second. You know, the derivative of natural log of x is 1 over x. And then plus the second, which is natural log of x, times the derivative of the first. And the derivative of x minus 1 is just 1. Now it's all about solving for dy over dx, right? So the next thing I'm going to do, let's simplify one more step. We'll simplify over here on the right. That's 1 over y times dy over dx is equal to, let's write that as x minus 1 over x plus the natural log of x, right? That means the same thing. Now, what I need to do is get this dy over dx on one side by itself, and to do that, I've got to multiply the left side by y and the right side by y, right? So this and this cancel each other out, and I have dy over dx isolated. So up here I have dy over dx is equal to y times x minus 1 over x plus the natural log of x. And we are almost finished. I know what y is. Remember, that was in my original equation. So I'm going to say my final answer way down here, dy over dx is y, which is x to the x minus 1 power, times x minus 1 over x plus the natural log of x. And that is my final answer. So again, whenever you have a variable raised to a variable power and you're asked to take the derivative, logarithmic differentiation is the way to go. This one direction said use it, but even if it didn't say use logarithmic differentiation, it said just calculate the derivative, you would be required to do it this way. Now that wraps up my first video for this section, which is bases other than e, taking derivatives and integrals. Part 2, I'm going to come back and we'll talk about integration of equations or functions with bases other than e. Hope you have a great day. Talk to you in a minute.